In January 2025, the Eaton fire tore through the hills above Pasadena, California. It forced the evacuation of one of the most important facilities in the history of human space exploration, the Jet Propulsion Laboratory, the building where the Europa Clipper mission was managed, the place where engineers had spent years solving problems that had never been solved before. The spacecraft had launched 3 months earlier. It was already in deep space, running on preloaded instructions, moving away from Earth at tens of thousands of kilometers per hour. And for several days, the team that built it could not talk to it. Not because of a technical failure, because their building was on fire. The chief engineer of the Europa Clipper mission described it this way afterward. It was like we had our baby spacecraft that just launched a few months ago, and now we had lost our ability to talk to it. The spacecraft survived. The mission continued. But that moment, a multi-billion-dollar spacecraft flying alone through deep space while its ground team evacuated from a wildfire, tells you something important about what it actually takes to operate at the edge of the solar system. And Europa Clipper, with all its complexity, with all the engineering innovations that went into building it, is only the beginning. It is the Scout. It flies past Europa 49 times and goes home with data. It does not land. It does not drill. It does not touch the surface. What comes after it, the mission that actually lands on Europa and attempts to reach the ocean beneath, is an engineering challenge so extreme that the scientists who have spent their careers designing it describe it, without exaggeration, as the hardest thing humanity has ever attempted in space. Let's get into exactly why. Here is the first problem, and it is not a small one. Jupiter has a magnetic field roughly 20,000 times stronger than Earth's. That field traps charged particles, electrons, and protons accelerated to enormous energies in a vast radiation belt surrounding the planet. The chief engineer of Europa Clipper described it this way: Jupiter has a giant donut of radiation around it, with Jupiter sitting right in the donut hole. Europa orbits within the donut itself. The radiation environment around Europa is the most hostile in the solar system outside the Sun. A human being standing on Europa's surface, with no shielding, would receive a lethal radiation dose in a matter of hours. Not days. Hours. Electronics do not fare much better. Standard spacecraft components, even radiation-hardened ones that meet military specifications, degrade rapidly in this environment. The energetic particles penetrate materials, disrupt electronic circuits, and corrupt data. Given enough time and enough exposure, they destroy everything. Building Europa Clipper to survive this environment required solutions that had never been used before. Engineers built a vault, a specially designed container made from 9.2 millimeter thick sheets of aluminum zinc alloy to house the spacecraft's most sensitive electronics. The vault adds mass. Mass is expensive to launch. But without it, the electronics would fail within weeks of reaching Jupiter. And even that was not enough. Just before launch, engineers discovered that some of the transistors used in the spacecraft systems were vulnerable to Jupiter's radiation at lower exposure levels than the military specifications said they should be. The components met the standard. The standard was wrong. Jupiter's radiation environment had revealed a gap in the industry's understanding of how certain transistors fail that nobody had known about before. The solution involved a canary box, a small device containing deliberately exposed samples of the vulnerable transistors, wired to detect degradation in real time. If the canaries die, the spacecraft knows its own electronics are approaching failure. It is an elegant solution to a terrifying problem. But Europa Clipper only spends a few hours near Europa on each flyby before retreating to a safer distance. The chief engineer described each approach as holding your breath. The spacecraft dives in, takes all of its observations, and gets out. A lander cannot do that. A lander stays. It sits on the surface, in the radiation, for the entire duration of its mission. Weeks, months, potentially years. The radiation shielding required for a long-duration lander on Europa's surface does not yet exist at the scale and weight that a practical mission would require. This is not a funding problem or a political problem. It is an unsolved engineering problem. The materials science needed to protect a lander and its instruments through months of continuous exposure to Europa's radiation environment is still being developed. And radiation is only the first problem. The second problem is getting to the surface in the first place. Landing on another world is one of the hardest things in aerospace engineering. Every landing we have ever attempted, the Moon, Mars, asteroids, comets, has required solving a unique set of problems specific to that environment. There is no generic landing solution. Every world is different. Europa is different in ways that make every previous landing look straightforward by comparison. The surface is ice, not solid rock like the Moon, not loose regolith like Mars. Ice, and not smooth ice either. Europa's surface is one of the most geologically complex terrains in the solar system. Tidal forces from Jupiter constantly flex the Moon, cracking the ice shell, pushing ridges upward, creating chaotic terrain that from orbit looks like a crumpled sheet of paper the size of a continent. Landing on that surface requires knowing in advance where a flat, stable area exists within reach of a target site. From orbit, Europa Clipper's cameras will map the surface in detail, but the resolution available from a flyby spacecraft, even a very good one, may not be sufficient to guarantee a safe landing site. You can see a flat-looking area from 25 kilometers up. You cannot see the meter-scale features that could tip a lander over on contact. A Mars landing uses the atmosphere to slow down. Parachutes, heat shields, airbags, sky cranes. Europa has no atmosphere. There is nothing to push against. A lander approaching Europa has to use rocket thrust alone for the entire descent, from orbital velocity down to zero, while navigating in a radiation environment that is actively trying to corrupt its guidance electronics. The descent has to be nearly fully autonomous. Because the one-way communication delay to Earth from Jupiter is 43 minutes, no human operator can intervene in real time during a landing that takes minutes from de-orbit burn to touchdown. Every decision, every course correction, every abort logic, all of it has to be pre-programmed and executed by a computer that is simultaneously managing radiation damage to its own circuits. NASA developed a prototype lander robot, tested on Alaska's Matanuska Glacier, specifically designed for Europa's icy terrain. It had 4 legs for stability on uneven ice, a stereoscopic camera system for autonomous navigation in low light, and a drilling tool called Ice Pick, capable of penetrating up to 27 centimeters into ice. It walked rather than rolled because wheels are useless on broken ice terrain. That prototype demonstrated that autonomous operation on an icy surface is possible. It also demonstrated exactly how many things can go wrong. The engineers testing it in Alaska described the 2025 field experiment as having all the pieces of a cryobot mission, just duct-taped together trying to see what breaks. What breaks in that environment is a useful thing to know before you spend $3 billion finding out on Europa. Even if a lander survives the radiation and sticks the landing, it faces the central challenge of the entire mission. The ocean is not at the surface. It is beneath 10 to 30 kilometers of ice. Let that number land. 10 to 30 kilometers of ice. The deepest ice core ever drilled on Earth at the Vostok Station in Antarctica reached about 3.8 kilometers after decades of drilling with industrial equipment weighing hundreds of tons. And that was on Earth, with a full support infrastructure, regular resupply, and humans on site making decisions in real time. To reach Europa's ocean, a robotic system has to penetrate ice that may be 2 to 8 times deeper than anything ever drilled on this planet, operating completely autonomously in a radiation environment that degrades its electronics continuously, communicating with Earth through a 43-minute one-way delay, with no possibility of repair or resupply if something goes wrong. The technology being developed for this challenge is called a cryobot. It is a heated cylindrical probe that melts its way downward through ice, refreezing the water behind it as it descends. Think of a hot needle slowly sinking through a block of ice, leaving no hole above it, carrying its instruments and communications equipment as it goes. The concept works in the laboratory. It has been tested in controlled environments. Research teams in Germany under the Triple Project are developing cryobot systems alongside underwater autonomous vehicles designed to operate in Europa's ocean once the ice is penetrated. American teams are testing similar systems, but the engineering challenges at full Europa scale remain immense. The cryobot has to carry a tether for communication back to the surface lander and eventually back to an orbiting relay satellite and eventually back to Earth. That tether has to survive the refreezing ice above it. It has to transmit data through kilometers of solid ice. And the entire system has to operate for months or years without human intervention of any kind. The NASA technical documents studying this problem note that just reaching 300 meters beneath the surface, not the ocean, just 300 meters, would constitute a scientifically successful mission. The ocean itself, at full depth, is a goal measured in decades of incremental engineering progress, not a single mission. And if and when a probe does reach the ocean, the mission enters its most extraordinary phase. Because what is down there has never been seen, has never been sampled, and may contain something that changes everything. Here's the part of the engineering discussion that the technical papers mention carefully and the press releases mention almost not at all. If Europa's ocean contains life, the mission to reach it becomes the most consequential and the most ethically complicated scientific event in human history. The concept of planetary protection has governed space exploration since the 1960s. The core principle is simple. You do not contaminate other worlds with Earth biology, and you do not bring unknown biology back to Earth without containment protocols that can handle something we have never encountered before. On Mars, planetary protection means sterilizing spacecraft components and carefully managing sample return. The protocols are complex and expensive but manageable because the probability of finding life on Mars, while non-zero, is considered relatively low. On Europa, the probability calculation is different. The conditions in that ocean, liquid water maintained for billions of years, chemical energy from hydrothermal vents, the organic chemistry that life requires, are among the best candidates for extraterrestrial life in the solar system. Scientists are not saying life is there, but they are not dismissing the possibility the way they once dismissed Mars. If a cryobot penetrates the ice shell and enters the ocean, it carries Earth microorganisms on its surface unless it has been sterilized to a degree that current technology cannot reliably achieve at the scale required. The heat sterilization methods used for other missions damage the electronics. The chemical methods leave residues. The radiation sterilization methods are incompatible with certain materials used in the probe's construction. And if the probe carries Earth life into an ocean that has its own life, the scientific contamination is irreversible. You cannot uncontaminate Europa's ocean once you have introduced Earth biology into it. The most valuable scientific sample in human history becomes unreadable. The planetary protection problem for Europa is currently considered unsolved. Not difficult, not expensive, unsolved. There is no method currently available that can guarantee the sterilization of a Europa cryobot to the standard that would be required for a mission targeting a potentially habitable ocean. This is why the official NASA position on a Europa lander remains cautious. Europa Clipper first. Characterize the ocean from the outside. Understand what we are dealing with before we decide whether and how to touch it. That caution is scientifically responsible. It is also, for anyone who wants to know whether we are alone in the solar system, extraordinarily frustrating. Here is the honest picture. The NASA Europa lander mission concept was formally shelved in 2025. Not because the science was unimportant, because the estimated cost of between $2 and $3 billion competed with other priorities in a constrained budget environment, and because the fundamental engineering challenges, radiation survivability, autonomous landing on ice, cryobot penetration depth, planetary protection, had not been solved to the degree required to justify a mission commitment. The hardware that was developed, the JPL prototype robot tested in Alaska, the ice pick drilling tool, the autonomous navigation systems, all of it remains. The engineering knowledge is not lost. It is waiting for the next budget cycle, the next administration priority, the next moment when political will and scientific readiness align. Meanwhile, the cryobot research continues in university labs and at international research centers. The German Triple Project, the American Orca program, small teams working on pieces of the puzzle with the funding available to them, building toward a capability that no single mission has yet been committed to achieve. Europa Clipper is currently in transit. It arrives at Jupiter in 2030. Its science phase, 49 flybys of Europa, begins in 2031. The data it returns will be the most detailed characterization of Europa ever produced. It will map the ice shell thickness. It will identify the most promising locations for a future lander. It will measure the ocean's chemistry indirectly through analysis of material ejected from the surface. And when those results come back, the argument for what comes next will be made with evidence rather than inference. The scientists who want to land will have the data they need to make the case. The engineers who need to solve the remaining problems will have the target specifications the data provides. The politicians who control the budgets will have the public attention that a confirmed potentially habitable ocean would generate. The question of whether we will eventually land on Europa and reach its ocean is not really a question. We will. The only variables are when and under whose flag, and whether we will have the wisdom to do it carefully enough not to destroy the very thing we came to find. The hardest thing we have ever done in space is still ahead of us. And everything we have built and launched and lost and rebuilt to get to this moment has been, in a way, we are only beginning to understand, practice. Next video covers the geopolitical race now accelerating between the United States, China, and private space companies to be the first to put boots on the Galilean moons, and why the timeline is moving faster than most people realize. I will see you in the next one.